Hi folks, thanks to be here for this talk about containerizing Java applications. I'm Nicolas Fränkel. I've been a developer for a long time. Now I'm a developer advocate, but more importantly, I'm interested in Docker and containers and Kubernetes. Nowadays, I work on the Apache API 6 project, and though this talk is not about Apache API 6, I suggest you have a look. Apache API 6 is an API gateway, and in this time and age, APIs are quite widespread. Suppose you are a Python developer. Then you have your Python script. Creating a Dockerfile for a Python app is quite straightforward. You inherit from Python, you install your dependencies, you run the script, and it's done. You can do the same with Node.js application, and it follows the exact same pattern. And all scripting languages, they follow the same pattern because actually there is no compile phase. Whereas in Java and other languages, you first need to compile your source, in that case to bytecode. So with scripting languages, it's what you see is what you run. Now in this talk, I would like to take this example of like a Java application that talks to an external service. In that case, it's Hazelcast. And so we will have this jar embedded in a container that we will run in Docker that will connect to an external service and do the stuff. So how do we create a Java app? Well, the easiest and most straightforward way would be to build the application outside of Docker and just wrap the jar inside of Docker. Let's do it. So here I have already created the project, and it's a simple Spring Boot project. As you can see, it's a web application. I'm using, as I mentioned, Hazelcast to use the client, and otherwise nothing mind-blowing. On the code side, I don't want to delve into too much detail, but basically we have two endpoints. The first endpoint allows us to store data into Hazelcast, and the second endpoint is to retrieve data. So basically, it's just a basic proxy to an external storage system. If we follow the strategy that I have mentioned, then we will create the jar outside of Docker and then wrap it. Here is the Dockerfile. Again, I believe it's quite straightforward. You just get the jar and then you say you want to run it. So first, let's build the jar. Here I'm using the Maven wrapper because it's much easier. Clean package. So the Maven wrappers allows you to automatically store Maven, like a copy, very small, shallow bootstrap of Maven. And yes, it's done. Now we just need to wrap this into the container. And here I'm using platform because I'm on the new Mac, and if I don't use it, then it won't work. And here I have it. Now we can run it. Let's not forget the port, 8080, 8080, and it's Spring in Docker 5. And now I need to start Hazelcast first, so Hazelcast start, otherwise it won't work. And I also need here to set the platform, and I forgot about it. And because there is a slight, let's say, translation between the normal chip and what I'm telling it, then it takes a bit more time than expected. So it has started, it has detected that there is a Hazelcast node running, and now we can try interacting with the application. I will do it only once because afterwards there is no point. So just curl localhost 8080, let's add data John. Yes, nope, it's X put or post, I don't remember. It's put, then I put another piece of data, Jane, yes, and now Yes, so I'm just using the application as a proxy. Data is stored. I'm super happy. Now there are a couple of issues with this approach, and the main issue is actually I'm building outside of Docker, and that I don't want to do. I want to have everything that is self-contained. So the alternative is actually to download the dependencies inside my build, to compile inside my build, and to build a jar inside my build. Just as a kind reminder, a jar is just like a zip with a specific structure, but nothing mind-blowing. Now the new Dockerfile, if we want to do everything, looks like this. We add all the resources, then we package, and then we run the stuff. So let's build this Dockerfile. And here we can see that I've already built it previously, so it's very, very fast. But the problem, so here you can see everything has been cached. If you are used to the old Docker stuff, now with BuildKit, it tells you explicitly what is cached and what is not. So here, for example, we can see that the last step, the thing about like packaging, meaning you create the jar was already being cached. What we can do is just add a single blank line. So here I'm adding a single blank line. And I rebuild. And now you can see that, yes, those resources are still cached, but the other are not cached. So it needs to do everything again. And in that case, the problem is it needs to like download the dependency. It's going to take a long time. So I will continue talking meanwhile it's building. So this approach has a couple of issues. First, in order to actually compile a Java code, we need to use a JDK and not a JRE, meaning that in the final image, we will have a JDK. So not only does it increase the size of the final image, it will also be able to compile other Java code that you pass to it later, which basically means it's a security issue because we don't want this image to compile after it has finished its build. As you've seen, I have to explicitly set the version every time. It might be a good thing for you, but this manual synchronization might create issues later on, because I would like, by default, that if I have a POM 1.0, I have an image 1.0. And now I have every time to think, oh, this is the POM 1.0, what should I type? And finally, as I've highlighted, if you change a single blank line, then you need to recompute everything, especially downloading the dependency. So it's about network, because there is no layering, there is a single layer. I've stopped the build because I already have the image, and let's see how the image is made. I'm using a tool called Dive, which allows me to check about the layers in the image. Again, it might take a bit of time. And here is how it looks. Here you can see the different layers. Here you can, like, this is probably from the parent image, and I started from here, where I copied resource by resource, and here you can see the build. And if we are interested in what each layer does, we can move to this view and don't see what has been unmodified. So here in the first layer that I've created, I've added the .mvn, which basically means I've added the Maven wrapper. I've added the command itself, the script. Here I've added the POM. Here I've added all the source, and here I did my stuff, which basically again downloaded all the dependencies and did everything afterwards, compile, package, whatever. So let's manage problems one by one. The first problem, I embed a JDK. That's again very, very bad. I only want a GRE. But of course, I need a JDK at the beginning to compile my code. So for that, the solution is pretty legacy. We will use multi-stage builds. Multi-stage builds allow you to have different steps like stages in your build file, and every time you can have a different parent image, and every time you can get files that were produced or existing in the previous image by referencing them. Hey, I want like this from this stage, I want to use this file. And the final image is the one from the latest stage. So actually what we can have is we can have a first stage with the GDK, the second stage with the GRE. The first stage builds, create the package, and we will reuse it from the GRE. An important thing is that if you are used to using Scaffold, and Scaffold is this nice tool that watches over your source, and every time you make changes, it rebuilds it and it sends it to a Kubernetes cluster, then this is not compatible with Scaffold, which in my opinion is the biggest problem with this approach. Otherwise, it's a pretty good thing to do. So this is the multi-stage build, and actually you can see here that I'm having two stages. The first one uses a GDK, as I mentioned, and I reference it as build. The second one is a simple GRE, and when this stage has been finished, I will take this file from this stage, so from the only one from the previous one, and put it inside this image, and then I can run it. Now, if we do this, it will work efficiently, but I remember there is this second problem about the layers. Every time I add a space or I change the source, I need to re-download the dependencies again. This is my bottleneck. So I want to improve this approach a bit. With this version, I already have something a bit better, because now I first copy all the resources and then I download the dependencies. Then afterwards, I copy source and I package. Meaning that if I change the source, then I don't need to download the dependencies again. This is the bottleneck. And for the rest, it's still the same. So let's dive into it. This is the view for the second image. The second image has been tagged. The first is just like an anonymous image. So we only see the final stuff copied target. And as you can see, it's very, very similar to the first one where we did the build outside of Docker. The only difference here is that we have a single Dockerfile and we let Docker take care of everything. We still have a couple of issues, even with this approach. And the problem right now is about versioning. We actually need to manually set the image name and in regards to the POM's version. And we would like this to be completely, like, let's say, in sync. Another issue is that we are using the jar like wrapper. So in Java, you can either like deliver jars, again, zip archives, or you can send a couple of class files and resources and libs and whatever. And the jar file has been our unit of delivery for a long time because it's very, very comfortable. But actually a Docker container is also a unit of delivery or a unit of deployment. So we have like a jar that like wraps our code, and then we have a Docker container that wraps our jar. So one of them is not really necessary. We could basically just add all the classes, all the resources, and rebuild the class path manually inside the Docker container. And that's what the people of Google thought about, and they created a plugin for that. So there is a Maven plugin, there is a Gradle plugin. It's called Gib, and this is exactly what it does. So it runs an exploded jar. At this point, I can remove the Docker file, and I just need to configure everything inside my POM. So I've added this Gib Maven plugin, and I can tell it from which image you should inherit. So I tell it about the parent, and you can use whatever you want. By default, it will use a specific, like distro-less parent image, but it depends on what you want. If you are more security-oriented, if you are more debug-oriented, here I want to have the exact same setup as before, so I'm using also the Alpine GRE, and then I can tag it accordingly. So I will reuse stuff from my POM. I will tell it, hey, use the artifact ID and the version ID. This is the command line, And here I need to call the Docker build target. Docker build target, we actually send the final image to the local Docker daemon. Of course, in general, you don't want to do that. You want to send it to a registry. There is another target for that, but you are required to set up the registry you want to send to, authenticate, whatever. So for the purpose of this demo, I will just send it to the local Docker daemon. In general, you don't use these targets, but here it's very, very good. Since I already built it, it's much, much faster than expected. And now we can dive into it. So here are my layers. You are now familiar. This is like the GRE. And we can see that by default, Gib already layered our Docker image. So at first, it sets the libraries because the libraries are the slowest. It's the bottleneck of the application to download the libraries. So it puts it at the top or at the bottom, depending on how you want to see it, but earlier in the build. Afterwards, it puts the snapshot libraries. Snapshot libraries can change over time, like quickly. Like with a regular version, you download a version 1.0 of a library, of a jar. It's supposed to be stable. It's supposed not to change ever. But snapshots are still under development. So actually they are less stable, and it makes sense to have them in a different layer. Then what can change is actually the resources of the application, the configuration file, the text files, whatever. And then finally you have the classes. So you have this like layering that is from the more stable to the less stable. And finally it adds on top its own stuff. Gib is a pretty solid solution, and I believe it's a good default. But we have a Spring Boot application, and Spring Boot also offers some interesting like way to build your Docker image. Spring allows you to create your own layers, which are slightly different from Gib layers, but it requires some more additional like manual process, and we need to get back to Dockerfile again. Here is my Dockerfile for that, and now we have 3 stages. The first one is the usual one, is we build the application, and again we still have our own layers inside the first stage. Then the second one is we take the jar that we created and we use like a specific jar to explode it. So we have this jar and we explode it manually, and this is very similar to what Gib did before. And then we are able to manually like use those like folders to layer it ourselves. So we have dependencies, snapshot dependencies. Here it's a bit different from Gib. Those are the same, dependency and snapshot dependencies, but here it's a bit different. So first there is a Spring Boot loader, so everything that is related to how Spring Boot will start the application, we put it in the third layer. And finally, classes and resources in the same layer on the top. I already built it because it takes quite some time, and now I just want to dive to show you how it works. So remember, we only see the latest stage. The container is just the latest stage. So again, this is the GRE, and here we can see our own layer. So those layers are the one that we like manually copied, like folder by folder. Dependencies, snapshot dependencies, the Spring Boot loader, and our application was, as I mentioned, I have the classes and the resources. An additional benefit of this approach, now we have a Dockerfile, which is not so great, but you can create your own layers. So if the default layers, you are not happy with them, if you have specific needs, you can create your own layer. And for that, there is this layer.index that you can customize. At this point, I need to tell about build kits and about mounts. If you are like an old Docker user, probably one of the biggest problems you had in your life was before you couldn't mount volumes during the build. And it was it would have been very practical. For example, you could have mounted the mvn/repository folder, so all the dependencies, you could have access to it during the build. Well, with build kits, it's now possible. It's very focused. You cannot do everything, but actually you can create caches during the build. The syntax is the following. You say, hey, I will mount with type cache, and you say the target. And for Maven, well, you just point it to the .m2 repository folder, and it will cache everything. And it works across builds. That's very important. So you could have two different builds. They will use the same cache, meaning that if a dependency has already been loaded once, you don't need to download it again. So all what I've told you so far about layers, they are now a bit less important, because again, the bottleneck is the download time, but if the dependency is already there, you don't care that much. Another approach would be to be using Buildpacks. I don't know how long you have been in IT, but if you did the cloud stuff a couple of years ago, like at the beginning, you might remember about Heroku. Perhaps you are already using Heroku. I am using Heroku still. And Heroku, the idea behind it is that you would provide the sources, and then you would push to their Git repository. When you push to their Git repository, it will try to sniff the type of project it was and build it accordingly. So it would recognize if it would be a Maven project, a Node.js project, whatever. And of course, it would say, hey, there is a POM, it's a Maven project, it's a package.json, it's a Node.js project, whatever. Of course, you could use like additional properties, but on its own, it would do like this sort of magic. And 2 or 3 years ago, VMware became interested in that kind of stuff. And they joined force with Heroku to create like a non-proprietary project to do that. Now this project is hosted by CNCF and it's named Buildpacks. It's exactly what it does. You like run Buildpack on your project. It's able to sniff what it is and build the correct container image like dedicated to this project. This is how it looks like. You need to install an external command line interface because again, it's not related to the project. And then you call it saying, hey, I want to use this base builder. Base builder will like sniff the project, use the correct parent image and run your stuff. I will try to run it. I won't wait until the end because it's going to take a long time. I still don't understand. Sometimes everything has been downloaded. Sometimes you need to download again additional dependencies. It's not, in my opinion, it's great if you are using a lot of different technologies and you want to have a single technology to build them. If you are a Java shop or a Node.js shop, it's more trouble than it's worth. It's still interesting. I will stop it and we will see how is the layer made. So of course it's a bit cryptic now. Like here there is nothing to tell us. We need to check everything. So it's up to you, but the important bits are at the bottom, like every time. So here we can see that it sniffed that it was a Spring Boot project, not only a Maven project, but a Spring Boot project. And it created the dedicated hierarchy and the right layers. Like we have this like boot.inf, which is very specific to Spring Boot. It's not meta.inf, it's not webinf, it's boot.inf. So it's specific to Spring Boot. Here we have the like loader, the classes that we have seen previously. And now we have our library, which is the snapshots. And then we have our own code. So both the classes and the files. And on top, we have specific like CNB is Cloud-Native Buildpack. So we have specific layers just to be Cloud-Native Buildpack compatible. So it adds at the top, again, at the top or at the bottom, like its own stuff. So you can run the container. As I mentioned, this like CLI is very good if you have lots of different technologies. You want to use a single command line interface to unify them all. But if you are a Java shop, like you are only have Maven application, then perhaps it's not that great because you need to install additional craft. But the Spring Boot plugin itself is able to leverage the same approach without the need for like an external tool. And it uses the Buildpack approach inside of itself. So we can create ourselves using Spring Boot build image, the container image in a Cloud-Native Buildpack kind of layer, but staying inside of Maven. And it is how it looks. Again, we have removed the Dockerfile, just as in the Cloud-Native Buildpack approach. We just say, hey, we want to enable the layers by default, and then we can just call Maven. So here, mvn wrapper spring boot build image. And now it does its stuff. First, it does the compilation, but everything, very important, everything is done inside of Docker. So again, you can see here it downloads the builder base, and that's interesting because yesterday I did the same, so it should be there. So again, it's the same issue as I mentioned in the like using the pack command line. I still don't understand when it needs to download a new image, but this is how it does it. It's going to take a long time, so I will skip it. So results will be pretty similar as with the pack command line interface. Now, one last point. So far, we didn't think about what we were doing. We were actually embedding a GVM inside a container. And remember that the GVM is really, really good to like optimize long-running processes. There is a mechanism inside the GVM that reads the bytecodes, and after some like optimizing cycle, once it has time to analyze the workload, it will create the best native code ever to handle this workload. That's the reason why with most performance benchmarks regarding the GVM, you need a warm-up time, and it might be quite long. So the idea of the GVM is to optimize long-running processes. Within a container, long-running might not be so long, because let's say that perhaps you are running in a Kubernetes cluster and you are running your container, and for whatever reason, then you don't have enough resources, this container needs to be killed, this pod will be killed. Or, again, it's stuck, and instead of trying to understand what happens, Kubernetes will just like unschedule it and schedule a new one. So long-running processes with containers, you need to be very careful about it. But GVM is optimized for that. So it takes more time to start up, more time to be efficient once you have startup, and this optimizing process takes a lot of memory. And in the area of cloud, perhaps you don't want that. So since a couple of years, there is a new project called GraalVM. GraalVM is a bag of tricks, but among one of them is the idea that at build time, you just compile your bytecode to native code already. So you don't try to optimize it in regard to the workload. You compile it and hope it will be for the best. You might not be like super efficient, but you don't run the GVM anymore. You run native code, which means less RAM and faster startup time. It depends a lot on your requirements, but the Spring Boot Maven plugin is able to create such like a native code container. For that, we need a couple of additional configuration. The first one is an additional dependency like Spring Native. The other is a plugin, AOT, which basically will help Spring create codes at compile time that GraalVM can easily understand, because Spring relies a lot on proxies and runtime magic. And here we want to make everything as explicit as possible for the GraalVM compiler to be able to work. And finally, if you are using the Spring Boot Maven plugin, you just add an additional env variable, native image, and it will create it. It's not unicorns and rainbows though. The biggest problem is that this like ahead of time compilation takes a long time. So really long time. It might be 5 minutes, it might be whatever. Depends of course on your project, on the complexity of the project, on your machine. But it takes a much longer time than your normal bytecode compilation. So you are like optimizing for runtime like efficiency, meaning quick startup time and not much RAM. And on the downside, it will take a long time to build and you won't be able to optimize the native code according to the workload. So recap. In this talk, I've addressed different ways to address the following problems. First, how you sync between the version in the POM and the version of the image. Second is how do you organize your layers so that if you change your source code, you don't need to re-download everything. So one way to do that is to organize the layers accordingly, and you need to think about it. So you need to understand how your tech stack, in that case Java, works, how Maven works. First, download the dependency, blah, blah, blah. Or if you are using build kits, and I think everybody now is running build kits, you can use cache mounts. And cache mounts is really incredible because you need to think less about layers, and you just say, hey, I want to like keep my dependencies like in a cache, and then you don't need to download them afterwards. Thanks a lot for your attention. You can read my blog if you're interested about the written part of this with the metrics, because I did some benchmark. I've created a blog post about that. You can follow me on Twitter. If you want to run the demo by yourself, everything is on GitHub. And though this talk was not about Apache API 6, I encourage you to have a look. Thanks a lot and have a good day.